Thank you. Hi, everybody. My name is Ken. I'm glad that y'all were able to attend today, and I appreciate all your participation. And I think this is a really good thing that what started last semester, and it's been a big success with a lot of speakers from several countries, and it's nice to have everybody here together for a seminar. So it's been a real nice series, and I look forward to the future on it too, and I look forward to today's talk with Dr. Bowie as well. And thank you. I hear that it's 2 a.m. I think we're in Australia, so I appreciate it very much, and I appreciate everybody for their attendance and all the speakers too. And let me give a special thanks to Professor Dean for organizing all this. It's really made it nice. While we're not always able to get together in a room, and it's even more special because we all get to be here together from different countries, and that's pretty impressive. So thank you for your good work on this, and we look forward to this semester. So I'll leave it there. Thank you.
Thank you, Ken, for your nice work. Now I think it's time to start. I would like to introduce Dr. Thế and Bùi. So please, I think it's your time. You can share your screen and then start your talk.
Okay. Firstly, I would like to thank you very much for your invitations to give the talk today. And today my talk is about the new Hardy spaces in harmonic analysis and applications. And firstly, I would like to let you know the outline of my talk today. That is, there are 3 parts. The first part is about the motivation, and then the main part, that is the Hardy spaces associated to operators. And finally, we will look at some applications. And before going to details, and I'd like to make some notations in my talk today. That is, we use dj here, that is the partial derivative with respect to the j variable, and nap là u here, that is just the radiance of u, and we use the notation that is minus delta for the Laplacians on Rn, and we also define the LB norm of the function from Rn to R like that. And if we have the weight here, and for the weight here, we just mean like the locally interval function on Rn. And for the weight here, and we also define the LB weight norm, like that. And we also recall the basic definitions about the boundedness of a linear or sublinear operator on the Banach space. And X is Banach space here, and we have the norm, that is the norm X here, right? And we have the sublinear or the linear operator T from X into itself. And we say that like T is bounded on X if we can find a constant C, and so that the following inequality holds true. And actually C here is independent of X. And let us move on to the first part, that is about the motivation. And our starting point is the Ritz transform on Rn. And the reason why we choose the Ritz transform, because the Ritz transform is the very common object in harmonic analysis, and maybe there are some applications in some problem in partial differential equations. And now for the Ritz transform on Rn, we shall mean the following operator. That is, we have the partial derivative, and that is just the fractional power of the Laplace. And for the fractional of the Laplacians, we can define via the Fourier transform, and the hat here, that is denotes for the Fourier transform. And therefore, if we take the power s here e power minus 1 over 2, and then we have that's e the modulus of psi power minus 1, and times the Fourier transform of psi. And in harmonic analysis, and we concern the following question, that's e whether or not the transform is bounded on LP for b between 1 and infinity. That's e whether or not we can verify the following inequality for all f in LB. And before going to the answer, and then we look at some applications of the grid transform. And now we have the following equation, and minus delta. I would like to remind that minus delta is just the Laplacian. And in this equation, and f here, that is the vector value function, the n components of f, and the divergence of f here is defined by that. And the function f here is the given function, and u is the solution. And if we know that like the grid transform is bounded on LP, and then when we take the derivative with respect to the j variable of u, and then we can write the formulae in that form. Okay, and now we just write the Laplacian power minus 1 into 2 fractional power with the power that is minus 1 over 2, and then we take the LB norm and we get the first inequality. And because the operator here, that is the composition of two operator, and then we just break this one into the product of two operator norm. Right. And you can see here, this one is the grid transform, and for the second operator, that is just like the minus of the conjugate of the grid transform. Therefore, if we know that the grid transform is bounded on LB, so that means the first term is dominated by a constant, and because the second term here is equal to the conjugate of this one, and when we take the LB norm, I mean the operator norm, right? And then we can see that like the first term is dominated by the constant, and so the second term. Therefore, we can write the radian of u if we take the LB norm and is dominated by the LB norm of the function f here. So this is just the regularity estimate for the solution to this equation. Therefore, you can see like the grid transform can imply the regularity of the solution to this equation. So that's one of the motivations of the grid transform. Okay, now we come back to the boundedness of the grid transform. That's the definition of the grid transform, right? And for the case p equal to 2, and if you check the Fourier transform, and then you can get this identity. And from this identity, and then we can see immediately that is the modulus of the Fourier transform of the f is equal to the modulus of the Fourier transform of f. And then we just use the very common property. That is, if we take the L2 norm of the Fourier transform of the function f, and then it is equal to the L2 norm of the function f, right? Therefore, we apply this property for the first inequality. And for the second inequality, just come from its identity. And then we have like the L2 norm of Tf is equal to the L2 norm of F. Therefore, we can imply that T is bounded on L2 or the drift transform is bounded on L2. Okay, and how about the case T is not equal to 2? And this case is more complicated, and actually that we can solve the problem by using the on-Zygmund theory. And for the on-Zygmund theory, I would like to give a brief overview of the on-Zygmund theory. And we have T here is the linear operator, and we assume that T is bounded on L2. And firstly, we define the associated kernel to T as is the function K defined on the product Rn times Rn, but excluding the case x equal to y. That means we exclude the diagonal. Or another way, we say that like function K is defined of diagonal on the product Rn times Rn. And the function K is called an associated kernel to T if the following identity is hold true. And I would like to bring your attention to the condition x doesn't belong to the support of F, because the problem that is x is undefined when x equal to y. Therefore, if x here in the support of F, and then the possibility that x and y here can be equal, but the function k here is undefined when x equal to y. This is the reason why we need this identity for x not in the support of F. And now we can define the on-Zygmund operator. That is, the on-Zygmund operator is a linear operator and bounded on L2, and the associated kernel satisfies the following two conditions. For the first condition, we just assume like the size condition of the kernel. And for the second condition, that is some continuity conditions, and we call that is the holder continuity condition. And this condition is stronger than the continuity condition, because you can see here, according to this inequality, and then you can see the kernel is continuous with respect to the first variable and the second variable. But we need a little bit stronger, that is the holder continuity. So we have some order delta here, right? And delta here, that is any number between 0 and 1. I mean, strictly greater than 0 and less than or equal to 1. And we assume that this one, whenever x minus x0 less than or equal to 1 over 2 times x minus y. Or another way, we can understand the condition just like when y is far away from x and x0. Okay, and for the on-Zygmund operator, and we have some known results. And firstly, that is the on-Zygmund operator may not be bounded on L1, but T is bounded from L1 to L1 infinity, and that is the definition of L1 infinity. But actually, please don't care about the formula of L1 infinity. We can use the following figure to illustrate for the statement here. That's it. You can see here. That's it, L1. Okay. That's it, the domain, and that's it, L1 here. And L1 infinity is some function space which is larger than L1. Okay. And because the on-Zygmund operator may not be bounded on L1, therefore we can find some on-Zygmund operator T and some function in L1. And when you check the image of F over T, we have TF here, and TF here is outside L1. Okay, but you still find like L infinity, so that you still have like the TF here, the E contained in the L1 infinity. Therefore, I would like to emphasize that we have the two nice properties for L1 infinity. That's the first one, that's the L1 infinity is large enough for the boundedness of the on-Zygmund operator. So we have T divided from L1 into L1 infinity. Yeah, and the second property is very important. That's the L1 infinity enjoys some interpolation property. And for interpolation, we shall mean if T is a linear or sublinear operator and T is bounded on LP for some P, P between 1 and infinity. For example, if we take T here is the Ritz transform, and then we know that like the Ritz transform is bounded on LP for P equal to 2, right? And if T is bounded from the L1 to L1 infinity, and then by interpolation, we can imply that T is bounded on LQ for all Q between 1 and P. So that's a very, very nice property. Without this property and then L1 infinity, make no sense, right? Because if we don't care about the interpolation theorem, and then you can take any lecture space and it still enjoy like the on-Zygmund operator bounded from L1 to the lecture space. But for the lecture space, maybe you lose the interpolation property. So that's the L1 infinity here. That is a very nice space. And the second property that we need to know, that is if T is the on-Zygmund operator, and then if you check the conjugate of T, so the conjugate of T is also a on-Zygmund operator. And to see that, we go back to the definition. Because Kxy is the kernel of T. Therefore, when you look at the conjugate of T, and then you can see K, Y, X, you just swap X and Y, and then you can get the conjugate, the kernel of the conjugate of T. Okay, and when you swap X and Y, and then you can see here, this condition is true. And this condition is satisfied as well. So this is the reason why we say that if T is the on-Zygmund operator, then T star is also a on-Zygmund operator. Therefore, we can, firstly, T is the on-Zygmund operator, and then T is bounded from L1 to L1 infinity. And by the assumption that T is bounded on L2. Therefore, if you combine this with this and the interpolation theorem, and then you can imply that T is bounded on LQ for all Q between 1 and 2. And then you check the conjugate, and then you have the conjugate is also bounded from on LP for B between 1 and 2, and then you go back to the operator T, and then you have T is bounded on LP for all B greater than 2. Therefore, you can see that if T is the on-Zygmund operator, and then T is bounded on LP for all P between 1 and infinity. So that is the very famous result due to Calder and Zygmund in 1952. Okay, and now I would like to move on to another endpoint estimate. Now go back to the figure here. You can see here, because we can find some on-Zygmund operator and some function, f, so that Tf is outside L1. Therefore, there are two ways we can modify the boundedness at the endpoint. The first one, that is we just enlarge the codomain, right? And then we have L1 infinity. And the other way, that is we can trim the domain. Or it's natural to raise the question whether or not we can find the suitable subset of L1. So that when you check the image of this subset, and then it's still in L1, right? So that's we can find the answer in this case. That's it. We can define the Hardy space, and the Hardy space is this one. Yeah, actually that is the proper subset, yeah, of L1, and T divided from H1, yeah, into L1. So we can illustrate by the following figure. That's G here, maybe TG, yeah, outside L1. But if we restrict, yeah, the domain here, that's in H1 here, so any functions, yeah, in H1 here, we can see like TF here is still in L1. And similarly, yeah, to the space L1 infinity, and for the Hardy space, yeah, we still have the interpolation. Okay, therefore the Hardy space here, yeah, is small enough for the boundedness of the Calder-Zygmund operator, but still large enough for the interpolation. Okay, therefore for the interpolation, yeah, we shall mean if T is the linear or sublinear operator and T bounded on LP for some P greater than 1. And if we know that T is bounded from the Hardy space, yeah, into L1, and we can imply that T is bounded on LQ for all Q between 1 and P. Okay, and for the Hardy space, yeah, I would like to give the very simple definition. Yeah, actually, there are the number of definitions, yeah, for the Hardy space. Yeah, but the very common, yeah, definition, that is we can define the Hardy space by the atoms. And for the atoms, yeah, we assume like 3 conditions. The first one, that is the support conditions. So we can find a ball, and so that the support, yeah, of A, yeah, it contained in a ball B. And that is the size conditions. Yeah, L infinity here, that is just a sensor supremum, yeah, of A is always less than or equal to the volume, that is the volume of B, power -1. And the last condition, that is the cancellation, the conditions are the vanishing moment condition. That is the interval, yeah, of AX equal to 0. And the Hardy space can be defined via the atomic decomposition, right? Yeah, just something like that. And the norm here is taken to be like the infimum of this one. And the infimum here is taken over all possibilities atomic decomposition for the function f. And if you look at here, and then you can see here, this is the Hardy space is the subset of L1. Okay, and for this reason, you can see like, yeah, H1 is always smaller than L1. Okay, now we back to the retrans form again. For the retrans form, yeah, we already know that like the retrans form is bounded on L2. Okay, and yeah, we just prove here. Let's see, for P equal to 2, and then the retrans form is bounded on L2. And actually, we can, by the simple calculations, and then we can verify that the kernel of the retrans form is equal to xj minus yj, and over x minus y, the modulus power n plus 1. Therefore, you can verify that the kernel satisfies this condition, right? And this condition as well. This condition for delta equal to 1. Okay, therefore, we can imply that the retrans form is a Calder-Zygmund operator. So if we apply the Calder-Zygmund theory, and then you can imply that the retrans form is bounded on LP for all B between 1 and infinity. And at the end point, P equal to 1, and then we have the retrans form is bounded from the Hardy space to L1. Okay, but the problem that is in practice, there are many operators beyond the Calder-Zygmund theory. And for example, we consider the following Schrödinger operator. For the Schrödinger operator, we just mean like we have the Laplacian, and then we add the potential to the Laplacian here. And the potential here, we just assume like non-negative and belong to L1 log. L1 log here, that is just means like V here is locally interval function. And now we consider the Ritz transform. That is, yeah, we just imitate the Ritz transform for the classical case. That is, we check the radon, right? And we check the fractional power, that is power minus 1/2. And we just replace the Laplacian here by L. And then we also have the Ritz transform of the Schrodinger operator. But now, because we do not have the Fourier transform, therefore we couldn't define the L power minus half via the Fourier transform. But we can employ some subordination formula, and then we can represent like L power minus 1/2 via the semigroup here, right? And therefore, we have the kernel of the Ritz transform is something like that. We check the radon of the heat kernel. That's it. BTXY, that's the kernel of this semigroup. Okay, and because the problem, that's it, V here is merely non-negative and belong to L1 log. Therefore, we couldn't expect the pointwise estimate for the radon of the heat kernel. Okay, and for example, we can take V here is equal to 1 over the modulus of x power 2 minus epsilon, and for some epsilon between 0 and 2. And then we can, it was proved by Sands in 1995 that the Ritz transform is not the on-Zygmund operator. Because the Ritz transform is not the on-Zygmund operator, therefore the Ritz transform might not be bounded from the Hardy space into the L1 space. So it's natural to raise the question whether or not we can construct like the new Hardy space for such operators. So that shows the need of the new function spaces. So that's the motivation of the problem. Okay, and now we move on to the main part of my talk today. That is the Hardy spaces associated to operators. Therefore, firstly, we need an operator. And for the operator in the talk today, we always assume that like L is non-negative self-adjoint operator on L2. And the kernel, BTXY of the semigroup E power minus TL satisfies the Gaussian upper bar. That's if we can find two constants, capital C and small c. So that this one is home true. And some typical example of operators satisfying these two conditions include the Laplacians. If we check L is the Laplacians, and then we can verify that the Laplacians satisfy A1 and A2. And we can check another example, that is L is the Schrodinger operator, and the potential here, that is greater than or equal to 0, and V belongs to the L1 log. Of course, apart from these two examples, there are still many examples of the operators satisfying A1 and A2 conditions. Okay, and now if we have the operator like that, and then in order to define the new Hardy space, then we need to review some equivalent characterizations for the Hardy space. And actually, there are many equivalent characterizations for the Hardy space that now I'd like to recall three of them. That is the first one, that is the Hardy space can be characterized in terms of the conical square function. And that is the vertical square function. Vertical because the interval here, just is with respect to t, and t from 0 to infinity. So if you can imagine that's it from 0 to t here, and the horizontal axis is Rn, right? And this interval, just with respect to t, so that's e from 0 to infinity, that's e we call the vertical square function. But for the first interval, if you sketch the region here, and then you can see here, it looks like the cone, okay? And for this reason, for the first square function that we call like the conical square function. And the final characterization, that is the maximal characterization. And among the three characterizations, and we just choose the first one. And we choose the first one, and we recall that by the Hardy functions, they can be characterized in that form, right? And the idea here is quite simple, and the idea here it comes from the on-Zygmund and Macquarie in 2004, and they just replace the Laplacian by L, and then they define the new square function, but associated to L, not the Laplacians, so this one, and therefore they define the Hardy space, let's see, all functions in L1, and the norm of the norm of f is defined by the L1 norm of SL, right? And because the Hardy space here depends on the operator L for this reason, and then they employ the notation that is H1L. And actually, like we mentioned before, and for the new Hardy space, and we expect a number of important properties for the new Hardy spaces. And the first one, that is the interpolation, and the second one, that is the atomic decomposition, and the last one, that is the endpoint estimate. And for the atomic decomposition, why the atomic decomposition is important? Because instead of working for the whole function in the Hardy space and via the atomic decomposition, and then we only work on the atoms, and working on the atoms is always similar than working on the whole functions in the Hardy spaces. And we need, firstly, for the interpolation, and the interpolation, we also have the following result due to on-Zygmund and Macquarie in 2004. That's if L satisfies the A1 and A2, and T is a sublinear or linear operator, and we assume that T is bounded on LQ, and for some Q between 1 and infinity. And if T is bounded from the Hardy space, the new Hardy space H1L to L1, and then we can imply that T is bounded on LP. For all, not for some, for all P between 1 and Q. Okay, and for the atomic decomposition, and then we look at the following example to see how the new Hardy spaces look like. Okay, and firstly, we look at the operator L, when the operator L here is the second order elliptic operator of the divergent form. So I mean, the operator L is defined like that, and Aij here is the real value function. Okay, and satisfies the following conditions. Firstly, if you form the matrix, Ax is equal to Aij, and this matrix is symmetric. And for the second condition, that's this condition is called the uniformly elliptic condition. That's we can find lambda greater than 0, so that we have this one and this one. Okay, and if you take by the AX here, there should be the identity matrix, and then you go back to the Laplacian. Therefore, in some sense, you can see like this kind of operator is a generalization of the Laplacian. And we just recall the definition of the new Hardy space, that is H1L. Okay, and this is very interesting. In this case, the new Hardy space and the classical Hardy space, they are the same. Okay, and we move on to the second example. The second example, that is, we consider the harmonic operator on Rn. For the harmonic operator on Rn here, that is, we shall mean like the Laplacian, and then we just add this term, that is the modulus of x, and the modulus of x square here, that is x1 square plus x2 square and plus up to xn square. Okay, and yeah, the harmonic operator is the very well-known operator in harmonic analysis and in approximation theory. And we can define the new Hardy space related to the harmonic operator. And now we will look like how the atoms of the new functions space here they look like. Okay, and to define the atoms, and we need to introduce this function. That's if we define pro x equal to the minimum of 1 and the modulus of x power minus 1. That means if the modulus of x is less than or equal to 1 and pro x is equal to 1. And if the modulus of x is greater than 1 and pro x is equal to 1 over the modulus of x. And we also define the pro 0 is equal to 1. And therefore, and now we can define the new atom like that. That is the support condition and the side condition. Okay, and just let you know, like for the first two conditions, they are similar to the first two conditions in the classical atom. So for the classical atom, and you have here, that is the support condition, the side condition, and the final one, that is the cancellation property, right? Yeah, but here, we have the support condition, the side condition, and for the last one, you can see here the cancellation condition just is required when the radius is less than or strictly less than the value of the function rho at the center, that is x0 over 4. I mean, if the bond with the small radius, and then we require this condition. Otherwise, if the radius is large, and then we can ignore it. Okay, and the number 4 here is not essential, that you can replace by any number you like. Like you can replace by number 2 or number 3, or if you like, you can replace this one by 2 times rho x0. So it's still the same. And then with the atoms here, and then we can define the Hardy space, the new Hardy space associated to the function rho. Okay, it's quite similar to the definition of the Hardy space. We just replace the classical atoms by the new atoms. Okay, and by the definition here, and then you can see here, the classical Hardy space is smaller than the new Hardy space. Okay, and actually, and the Hardy space defined by the new atoms here, and the Hardy space defined by that, and they're equal. and they are the same. And this result is due to Lesbesgue in 1995. Okay, and for the last example, we consider two vector operators. And for two vector operators here, we shall mean like L is equal to this one and L equal to this one. And the parameter nu here is greater than -1. And I'd like to emphasize that now we just can restrict ourselves to consider on the interval 0 and 1. Not like the whole space, right? And the difference between the underlying space here, that is the measure, and that is the Lesbesgue measure, Tx. But here we have the weight, x power 2 nu plus 1. Okay, and that is just something like the formal definitions of D2 operators based on the eigenvalues and the eigenvectors, and we don't need to go into the details, and we would like to omit the detail here. Okay, and for this kind of operator, okay, and of course we can define the new Hardy space like that. Because here we just restrict on the interval 0 and 1. Therefore, the interval here we should restrict ourselves to consider like from 0 to 1, not 0 to infinity like the case before, right? And now we also define we need to construct the following interval j sub j. Okay, and if you look at the formula here, so maybe it's quite confused. But actually, if you look at the diagram here, and it's very easy to consider the intervals. Firstly, we have the interval 0 and 1, right? And then you take the midpoint, that is 1 over 2. And we have the two sub-intervals, that is 0 and 1 over 2 and 1 over 2 and 1. And for the first interval, sub-interval 0 and 1, you take the midpoint, that is 1 over 4. And then you take this interval to be j minus 1. Okay, likewise, for the second interval, you take the midpoint here, right? And you take this interval to be j1. And likewise, you just take the midpoint here, and then you can contract, that is j2. And you take the midpoint here, and then you have j minus 2. And keep going, and then you can get all interval j sub j. And with the intervals on hand, and we can construct the new type of the atoms. So we distinguish by two types. That is type A. Type A here, just simply like the classical atoms, right? That is the support condition, the sign condition, and the cancellation property, or the cancellation conditions. But for type B here, we can specify the atom, the atom should be in that form. And psi here means the characteristic functions of the interval j sub j. Okay, and then we can define the Hardy space via the atomic decomposition. And then we also show that like if nu here is greater than minus 1 over 2, and then the Hardy space associated to the operator L and the Hardy space defined via the atomic decomposition, and they are coincide. Okay, and at the beginning we emphasize that like nu here should be greater than minus 1. Therefore, I would like to explain about the restriction here, or the limitation here, Let's see, because for nu here greater than -1, and then we have the hit kernel, yeah, like that, and we can prove that the Gaussian estimate, yeah, fails when nu here is less than or equal to -1/2, and this is the reason why, yeah, we need nu here is greater than -1/2. And for the second Bexel operator, yeah, that's this kind of operator. They're still on the interval 0 and 1. Let the measure here, let's see, change a little bit. That we have the weight here, that's the x power 2 nu plus 1. And then we define something like that. Yeah, we just change here, let's see, instead of dy, yeah, we replace by the new measure. Let's see, d mu here is equal to this one, we replace by the new measure. And instead of the term t power n plus 1, and we break into t times the measure, yeah, of the bone center x radius t, right? And if you remember that if mu here is the Lesbesgue measure, and then you have the volume here equivalent to t power n, therefore we go back to the case by t power n plus 1. Okay, and now we define the interval like that. Let's see, we have 0 and 1, right? And then we take the midpoint, and we take the sub-interval on the left-hand side. Let's see, I0. And for this sub-interval, yeah, we just take the midpoint here, and then we take the sub-interval on the left-hand side, and then we set, let's see, yeah, I1. And then check the midpoint, and we have I2, and then we can construct, yeah, the intervals, yeah, Ij. And we also, yeah, define the atoms, yeah, like that. There are two kinds of atoms. Yeah, the first atom, that is quite similar to the classical one, right? We have support condition, side condition. Yeah, but we replace the Lesbesgue measure by the new measure, that's in mu, right? And we replace, yeah, the integral with respect to dx by the integral with respect to d mu, and equal to 0. And for the atom, yeah, in type D, yeah, that is the characteristic, yeah, function, yeah, of Ij, and over the measure of Ij. And we also define, yeah, the Hardy space via the atomic decomposition, yeah, with the new atoms. And then we also show that the Hardy space, that is 2L, and the Hardy space, yeah, defined via, yeah, the new atoms, and they are the same. Okay, and I would like to move on to the first part, that is some application, and we will consider some application here, yeah, to see how we have the endpoint estimate. Okay, and L here, I recall that L here is satisfies, yeah, A1 and A2, and M here is the bounded function, and we can define like this operator, and operator is known as like the spectral multiplier, yeah, of the Laplace transform type. And the reason why they consider this kind of operator, because this kind of operator includes, yeah, the imaginary power. And for it, the imaginary power of L here, that is the very important operator in harmonic analysis and in PD. And by the spectral theory, and then we have, yeah, ML is bounded on L2. Okay, and for the endpoint, and Jung and Jan in 2010, yeah, proved that, yeah, ML is bounded on the Hardy space, yeah, H1L. Okay, it means, yeah, we have the following, yeah, inequality. And actually, yeah, because the Hardy space, the new Hardy space is larger than, sorry, is smaller than the L1, and then yeah, it estimate yeah, implies the following inequality. So it means that like ML here is bounded from the new Hardy space into the L1 space. And the second the second application, that is we go back to the harmonic operator. And for the harmonic operator, and we consider the higher grid transform. Okay, for the higher grid transform here, we assume like M here, that is the natural number, and alpha is the Monty index, yeah, and the modulus of alpha equal to M. And for example, if you take M here equal to 1, and then you see here, that is just the partial derivative, the first order, right? And H here, that is H power minus 1 over 2. And that go back to the first order grid transform. And in 1993, and Young, yes, so that the grid transform, the higher order grid transform is bounded on LP for ohm P between 1 and infinity. And now Jung and I in 2020, they proved that like the higher order grid transform is bounded on the new Hardy space. And actually, because yeah, we have the new Hardy space here is larger than the classical Hardy space. Therefore, yeah, we can imply, yeah, this one is imply, yeah, the higher order grid transform is bounded from the new Hardy space, yeah, to the classical Hardy space. And because the Hardy space here is smaller than L1, and then it also implies, yeah, the boundedness, yeah, from the new Hardy space, yeah, into L1. And now I would like to end my talk by considering the following applications of the higher order grid transform. That is, if we consider this equation, right, and then formally that we can write U equal to H power minus 1 zeta F, because this one is H, and when we bring this operator to the right hand side, and it's going to be like H power minus 1. And if we look at the second order derivative of U, right, and then we have this one. And now the middle term here, that is just the second order grid transform. And we also prove that the second order grid transform is bounded on the new Hardy space. And so we get like something like the regularity, yeah, estimate, yeah, of the solution to this equation, yeah, on the new Hardy space. Okay, thank you so much.
Thank you very much. So do you have any questions for our speakers? Okay, I don't hear any questions. I have a couple questions for you. Like,
okay.
So the main purpose of this is to let's say to create new Hardy spaces, right?
Yep.
So do you compare what kind of Hardy space is good, which is not good, and how to see that? Like, of course, you use some operator, you consider some operator, and then you use that bounded operator to create new Hardy, right? New Hardy space.
Yep.
So how do we know that the new one is good?
Yeah, the new one is good. Yeah, because like for okay. For example, yeah, if you can, yeah, can you see my screen now?
Yes, yes.
Okay, for example, if you can consider like this kind of operator, and then you cannot replace, yeah, the new Hardy space here by the classical Hardy space. that's it. It's not clear whether or not you have like the ML. Yeah, sorry, that's the MLF. You have L1 norm here. I mean, you cannot replace H1L here by H1. Yeah, that might not be true. Therefore, it means that the classical Hardy space doesn't work in this case, but the new one work well. Right, and if you look at here, and you can see here, because H1, H here, the new Hardy space here is larger than H1, right? Therefore, this one is better than this one.
Okay, so the norm is smaller, right? As you said.
Yep.
And, okay, so that is the main criterion to create new Hardy space.
Yeah, because like in some Schrodinger operator, and then when you consider some singular intro like the Ritz transform, and maybe for the classical Hardy space, and then it doesn't work well in this setting. But when you replace the classical Hardy space by the new Hardy space, and everything is okay.
Okay, and so second question is, yes, that is on your slide. So you consider LP when between 1 and infinity. So what is the situation between 0 and 1? I think that is extremely difficult.
Yeah, right. Actually, we can define the Hardy space for P strictly less than 1 and very close to 0. But like because for the sake of simplicity, so I just represent like the case P equal to 1. Right. Okay. And actually, the theory here can be developed for the case P greater than 0 and less than or equal to 1.
When you consider a Schrodinger operator with Bessel potential and associated Hardy space, when the value of nu hits 1/2 and you lose on your potential, so you should be getting like a classical Hardy space there, or what happens there?
Okay, because the problem that's it. When we consider the Ritz transform, for example, right, and then we can write the kernel in that form,
right,
and that's either radon, and that's either hit kernel. You have the Schrodinger operator, and because V here is merely non-negative, and maybe not smooth enough, and maybe we cannot expect that we can estimate about, the point-wise estimate for the kernel here. And then we can point out like one example. If V is equal to this one, and then the Ritz transform is not the on-Zygmund operator. Because like if V here is very smooth, like if you replace V here by the polynomial, and then maybe kxy here enjoys some property of the on-Zygmund kernel. But the point here, if V here is not smooth enough, and then maybe we cannot get the point-wise estimate for the radon of the hit kernel.
Okay.
Yes.
All right, thank you.
I still have one more question, because almost everywhere you consider bounded operator, right?
Yep.
So what happens if you have unbounded operator? Can you like create a new Hardy space associated to unbounded operator? Maybe that question may not make sense. I don't know.
Actually, for the second order elliptic operator of divergent form here, if we relax this condition, and then we allow Aij here to be the complex value function, and then in this case, if we consider like the Ritz transform, and the Ritz transform of this kind of operator just is bounded on LP for some range of B is very close to 2. Yeah, not bounded on LP for P close to 1. Yeah, but we still can construct the Hardy space, so that the return form we bounded from the new Hardy space into L1. But in this case, when we apply the interpolation, and then we cannot get like the full range of B, we just like get like P greater than B0 and less than or equal to 2. That makes sense.
I see.
Yeah, and definitely because in this case, this operator is not bounded on LP for P equal to 1. Therefore, the classical Hardy space cannot be applied for this, the return form of its operator.
Okay, thank you. So do you have anything else for him? So if not, let's thank speaker again for his interesting talk.
Thank you so much.
Yeah, thank you very much. And using this case, I would like to announce that our next speaker is Dr. Ingis Kayumo from Kazan State University. So the next talk will be earlier a little bit, so on 1 hour, because I will send out another announcement about this. Okay. So finally, I would like to say thank you again for joining us, and have a good evening, especially for people in Asian Russia, and you have a good night, Dr. Taean.
Okay.
Good time of the day.
Bye bye. See you.
Thank you.
Okay, bye.
Bye. Thank you.
Thank you.